Okay, so what we are talking about is in one dimension the standing wave looks like this. Why is it standing wave? As we said, because standing waves are such, for example, like this one, it goes to 0 here, it goes to 0 here. So that means you have to ensure that for all those waves, another wave, for example, suppose like this, this, and things like that. So they will form something like this. So okay, so it goes to 0 here, it goes to 0 here. So that means for all those k, n equals to 1, n equals to 2, for all these conditions, this function will go to 0 irrespective of the time. So at every time this point will go through a 0. That means the nodal point does not seem to move, so the wave motion looks like a standing wave, it is not moving. Okay, because at all time, because these are the conditions at which k, at this x, for different k values, it satisfies the condition that kx equals to n pi for different x. Okay, so then automatically it becomes 0 in those points, and that behaves like a standing wave. Now those are the waves which supposed to survive, so we'll have to estimate what are the number of modes with these different possible frequencies, how many such modes are possible. So for that, let us consider in 3 dimension again, then the condition becomes k dot r. So k is a vector, so let us consider that k is equals to ikx plus jky plus kz. Okay, and then that r is equals to vector equals to say ix plus jy plus kz. So the dot products will have, so imaginary part of that will represent the wave, right? The imaginary part. So imaginary part, this part is real, this part is suppose real. So imaginary part of e to the power I k dot r essentially will matter, and that turns out to be imaginary part of this, and that turns out to be sine of x kx plus sine of y ky plus sine of z kz. Okay, now these things has to be 0. When these things become 0 for a standing wave, that is the condition that at boundaries these waves should vanish, amplitude should vanish, and that automatically will be taken care of provided the conditions are like that. X equals to L, y equals to L, z equals to L we are putting, and then del Lkx should be equals to say nx pi, where Lky is equals to ny pi and Lkz equals to nz pi, where nx, ny and nz has the values of 1, 2, 3, etc., all positive values. Okay, now given this, symbolically this can be collectively represented as this equals to pi by L n. Okay, so this is the condition for which you will have standing wave. Now let us get into the other thing, following analysis further. Okay, so given this, we can say that k square, so see what we have, it is like this. So k square can be written as pi square by L square into n square, and n square equals to nx square plus ny square plus nz square. Okay, now again that the similar kind of analysis as we did for free particle in a box for translational modes, in this case also, for example, we consider that only the positive quadrant of an n space sphere, okay, of this kind. So this is suppose nx direction, this is ny direction, and that one is nz direction, and you have all those values 1, 2, 3, etc. then we have to find out how many such possible combinations of nx, ny and z we can accommodate in this sphere of radius r, where r we will consider as the radius r, so that r square is equals to nx square plus ny square plus nz square. Just it is a technique that we are using, the similar kind of technique. So r square, if we consider this as r, then r square is equals to L square k square by pi square. So the sphere, the positive quadrant of the sphere, if we consider, so the number of waves with their magnitude of wave vector k between say k and k plus dk, between 0 and k, suppose symbolically we represent as phi of k, and that phi of k will be then what, 1/8 of 4 by 3 pi r cube, and r cube we are writing it as 3 by 2, like that, because r square we have a ready-made relationship. Okay, so 1/8 because only the positive quadrants are involved, and then divided by 1 in principle, which I have not shown. So this gives you the total number of such modes with different combinations of nx, ny and z that can be accommodated with the maximum value having k, and starting from 0 to k. What are the number of modes that possibly will survive as a standing wave? Other k values which do not follow this condition, that n pi equals to kl, any other k values which does not fall in this category, all those waves with those k values will ultimately not survive, and they will not produce the standing waves. So there are some restrictions. So this helps us to estimate the kinds of, or the number of standing wave modes that is possible in that crystal. So given this, we can just substitute it as 1/6 pi and then kl by pi to the power cube. Okay, so that it comes to, and then given this omega k dk, that will be the number of say normal modes having wave vector magnitudes between k and k plus dk. So it is essentially kind of that density of weights, density of wave that we are talking about in the translational function case. So it is basically similar. So this is d phi by dk, and that we can do it easily, and that L cube is V, so it turns out to be V k square by twice pi square dk, right? So this is pi cube, I think, right? No, there is a pi here, so that's pi square dk, right? That's fine. So given this, now, so that is my omega k dk. Now one thing we have to do is we have to find an equivalent from here in terms of nu. And how do we find in terms of nu? The whole function, we know that k equals to 2 pi by lambda, and that can be written as 2 pi nu by v, where v is the velocity of the wave. Now given this, we can just substitute it properly. Okay, so all k should be replaced by this. So omega k dk is this, so that equals to v, and k square means 2 pi nu by v whole square, and then you have 1 by 2 pi square already there. So k square is this, and dk is 2 pi by v d nu. So in terms of frequency, the whole thing now looks like you have v cube in the denominator, and 2 pi gets cancelled, so you have 4 pi v. This v is the volume of the crystal, 4 pi v and nu cube